This is AP Calculus BC, and in this video I'm going to talk about section 5.3, which is integration by substitution. So the big thing about this section that we need to be thinking about is that essentially what we're going to do today is we're going to start integrating more complex functions, and what we're really taking into account here is the chain rule. We're sort of doing the opposite of the chain rule when we do an integration by substitution. So I'm going to show you an example of how this works, and then I'll go through the process for this. This can be a little bit challenging at first. This is one of those things that the more you do it, the easier it gets. Part of the reason that this is really challenging is because a lot of times on these problems, you're going to have a lot of options available to you, and you have to think through the process a little bit before you just jump into it. Okay, so let's take a look at how this works. So remember last time when we went through integration, we were doing those indefinite integrals and we had really, really simple antiderivatives. Well, most of the time when we're dealing with functions, they're going to be a lot more complicated than that. And when we need to integrate things that are a little more complicated, we have to have different methods that we can use. And the first method that we have available to us is called Usubstitution. So you can see the function that we're trying to integrate here is x squared times the square root of 5 plus 2x cubed. Okay, so we want to integrate that function. Now, that looks a lot messier than what we did last time. We can't just look at that and know the antiderivative, or at least most of us can't do that. So what we're going to do is we're going to define part of this function that we're trying to integrate to be a u expression. And you can see over here it's been defined. We're going to say u is equal to 5 plus 2x cubed. And then we're going to find an expression called du. And really what I'm doing here is if I take the derivative of u with respect to x, I get 6x squared. And then I can multiply the dx over to the other side, and that's where the du comes from. Okay, so the reason we're doing that is because we want to rewrite this integral that looks really hard to integrate, hard to find the antiderivative of. We want to rewrite it in a form that makes it very, very easy to work with. And so what I'm going to do here is I'm going to substitute in for this 5 plus 2x cubed. I'm going to make that u. And then in order to finish off my substitution, I need to be able to replace the dx in this as well. So what we've done here is, notice that for our du, we need to have a 6 times x squared dx. Right now, we only have an x squared. But what we can do is we can rewrite the 1 that's in front of the x squared as 1/6 times 6. And then constants can move in and out of the integral. That was one of the properties that we looked at last time. The constants have no impact on the integral. So I haven't changed anything about my integral on this second step, except for the form that it's in to make the substitution work out. So now I've got the square root of 5 plus 2x cubed becomes u to the 1/2. The 6x squared times dx is my du. So notice that du has been placed right there. Okay, so now the 1/6 is still out in the front, but now look at the integral that I started with. Really, really difficult to work with. Now think about, how do I take the antiderivative of that? And it's just simple power rule now. So we add 1 to the exponent, divide by the new exponent, and we just have to remember we have this constant out in front. So I multiplied by the constant here. And in the end, well, I don't want my solution to be in terms of u. I want my solution to be in terms of x. So the last thing that we do here is take our u expression and plug it back in for u. And now I've got the function that is the antiderivative of x squared times the square root of 5 plus 2x cubed. Again, just like before, if I want to check it, I can just take the derivative of that, and you would see that you get what we started with. Okay, so this process, like I said before, it can be a little bit challenging at first, but you will find that the more times you do it, the easier it gets. Okay, so let's practice with this a little bit. On these first few problems, you're going to be supplied the u expression. That's usually the hardest part of these problems, is figuring out what does u need to be. So on these problems, they gave you the u so that you could just focus on the mechanics of solving this out. So they're saying we've got sine of 3x. Let's let u be equal to 3x. That means my du would be 3 times dx. Okay, so if that's the case, I need to have a 3 in my integral to be able to do this substitution. So I'm going to rewrite this integral as 1/3 times the integral of 3 sine 3x dx. Now remember, the 1/3 and the 3 multiply to make 1, so I haven't changed anything. I'm just trying to make my substitution work out. So now let's do the substitution. This is the same as 1/3 times the integral. Sine 3x becomes the sine of u, and 3 dx becomes du. And now all I have to do is the antiderivative of sine, which would be negative cosine, so I get negative 1/3 cosine u plus c. And my final step here, I want to replace that u, so I'm going to get negative 1/3 times the cosine of 3x plus c. And again, I can easily check that, just take the derivative and see if I get what I started with. Okay, so it's not really that difficult when you're given the u. Now, the next 4 problems in these notes, you're given the u. So what I want you to do is just pause the video, try to practice with this process a little bit. Get the du, figure out if you need to manipulate the original integral at all, and then work out the problem from there. So pause the video, take a couple of minutes and work those out, and then I'll show you the solutions. Okay, so here are the rest of these. The next one, we had u was 2x squared, the du was 4x. We didn't have a 4 in the integral, so I put a 4 in there and put a 1/4 on the outside. If you notice this time, I didn't rewrite the integral. I just wrote it on the given integral just to save myself an extra step of writing. I'm perfectly fine with you doing that when you're given an integral that you can actually write on. With us operating in the virtual way that we are right now, it's going to be a little bit more difficult to do that. But when you are actually working on, a test like your AP exam, for example, you can actually write it on there and just save yourself that step. Okay, so I've got everything in there that I need. So I did the substitution, and it just became the integral of cosine of u, and the antiderivative is sine, and then just plug back in for the sine, or excuse me, plug back in for the u. So pretty simple. The next one here, you can see that with the du, I need to have a 7 times dx. Well, even though the coefficient out in front here is a 28, 28 is 4 times 7, so there is a 7 there. I just need to get the 4 out of the way. So I factored the 4 out, left the 7 in, and then I can do my substitution. This becomes u cubed, and then it's just the antiderivative using the power rule, u to the 4th over 4 times 4, and then just plug back in for the u. Okay, so again, very, very simple once you understand this process. Here we've got 1 minus r cubed, so my du is going to be negative 3r squared dr. You can see that we've got a 9 in the numerator right now. So even though there's not a negative 3 sitting in front of me, there is actually a negative 3 there because 9 is negative 3 times negative 3. So I just factored out a negative 3 and left the other negative 3 inside the integral. And this whole integral can be simplified down into u to the negative 1/2. And then from there, it's just power rule and make sure you substitute back in for the u. So again, pretty simple to do. The last one that you had where the u was supplied was this one. And we had u as cosine x, the du is negative sine x dx. So in the original integral, I didn't have a negative sign. So I put a negative in there, which means I need to put a negative on the outside so that it multiplies together to give me the original integral. And this is just e to the u once I do my substitution. So we know the antiderivative of e to the u is e to the u. And then just substitute back in for the u. Okay, so again, very, very simple when the u is supplied. Now, let's take a look at some practice problems. Primarily what we're going to do the rest of the way here is work out some practice problems. So on these problems, I want to go through one of each type with you so you can get a feel for how these work. So these are what we call easy to recognize substitutions. Even when these are easy to recognize, I don't want you to immediately jump into a problem. What I want you to do when you see one of these problems is what we talked about when we see derivatives. After we knew a lot of derivative rules, we started to have a lot of options available to us. So instead of just jumping into the problem, we want to think about what can I do to solve this out? What are the options that are in front of me? So here, I've got the square root of x, or excuse me, I've got the integral of x times the square root of 1 minus x squared dx. So in my mind, I'm thinking, okay, what can I make my u? And before I write that down, can I get the du that I would need to show up? Okay, so in my head, I would be thinking, all right, probably I want u to be 1 minus x squared. If that's the case, that means my du needs to be negative 2x dx. And I don't have a negative 2x dx, but I do have an x. And I know if I just need a constant, I can make that constant show up. So once I've gone through that process in my head, now I know I'm going down the right path. I know this is going to work. So my du here is negative 2x dx. Okay, so again, work that out in your head in advance so that you just don't start working through the problem, get 3-4 steps in, and then realize, oh, this isn't going to work, and then you have to start over again. Okay, so I need a negative 2 in here. I can't really squeeze that in, so I'll just rewrite this. This would be the same as negative 1/2 times the integral of negative 2x times the square root of 1 minus x squared dx. So when I do my substitution, this is just going to become negative 1/2 times the integral. The square root becomes the square root of u, or u to the 1/2. The negative 2x dx becomes my du. Okay, and then from there, once I've got that substitution done, if I've done it correctly, I should have turned this into something that's very, very easy to solve. And in this case, you can see I can just use my power rule. So this is going to give me 2/3 u to the 3/2 and then plus c. So in the end, when I do my substitution back in for the u, I'm going to get negative 1/3 times 1 minus x squared to the 3/2 plus c. Now, one question that I often get is on this step, why did I not multiply the negative 1/2 over to the c? And the reason I didn't is because c is an arbitrary constant. So no matter what I do to it, if I multiply, if I divide, if I add, or if I subtract, if I do anything that involves a constant to another constant and it's arbitrary, it's still an arbitrary constant. So even though I'm multiplying c by negative 1/2, it's still an unknown value. So I'm just going to continue to call it c. So that's why the c didn't change. I could technically write minus 1/2 c as my solution, but it's just not necessary. We typically just have the arbitrary constant just absorb whatever is being multiplied or divided or added or subtracted. Okay, so there are several more of these problems. 1, 2, 3, 4, 5, 6, 7, 8 more of these that I want you to do. So there's 5 here and then 3 on this next page. When you get to the less apparent substitutions, just stop for now. But what I want you to do is pause the video and try to work through those 8. And remember, think through the process. Don't just jump into it every time. Think through the u and then try to decide, can I make that du show up? And if the answer is yes, then that's probably going to lead you down the correct path to a solution. So pause the video. When you come back, I will show you the solutions. All right, so here's the next one. You can see my u was 4 plus x squared. My du is 2x dx. And you can see with my substitution how this worked out. It's not really anything too tricky on this one other than, you know, the way I wrote my answer, I wrote it as a 1 over u. I don't want to use negative exponents in my answer. For this one, whenever you have an x to the first power in the denominator, that should be making you think of natural log. So my u in this case was 2x minus 3. My du is 2 times dx. So I didn't have a 2. I put a 2 in and 1/2 on the outside. The only thing on this one that I want to point out, notice that in my solution, I did include an absolute value here. So I used absolute value of u and I used absolute value of 2x minus 3. That's, again, like I mentioned earlier on the previous video, it's because I don't have any domain restrictions here. So if there's no domain restrictions, I need this to work when I have values that make 2x minus 3 negative. So that means that log, for the natural log piece of this, I've got to include the absolute value. All right, for this one that's cotangent, this is where these start to get kind of tricky. When you involve the trig functions, you really start to open yourself up to a lot more possibilities. So first thing I would think of here is there an antiderivative for cotangent? And there's not. So then I have to start thinking about what are different ways that I can manipulate this trig function to get it into a form that's going to work. So I rewrote it as cosine over sine. And then from there, you can see that my u is sine 7x and my du is 7 cosine 7x dx. Now remember, this dx is attached up here in the numerator, right? So even though it looks like I might be able to choose either one of those to be the u, I really had to choose the sine x to be the u because the dx is attached to the cosine. Anyway, once you recognize that, this is another natural log, and you can see that I put an absolute value as part of the solution there. All right, so for this one, dx over cosine squared 2x. Sometimes on these, you won't even need to use substitution. This is a good example of that. So recognizing that 1 over cosine squared is the same as secant squared, you could, if you really wanted to, force this to be a substitution and say u needs to be 2x and your du is 2dx, and you'd end up with the same result. But if you can skip over the substitution steps on these simpler problems, you definitely want to get in the habit of doing that, since this actual process will be a very small piece of what we do when we get into problem solving. This would be like one step out of a 10-step problem. All right, so again, here's another trig function, and this one's a little harder. So we have cotangent squared 3x. So there is no antiderivative for cotangent squared 3x, at least not in the form that it's in. So I tried to think about maybe cosine squared over sine squared. That doesn't work. And then I thought, okay, well, let's try a Pythagorean identity. Well, when I do a Pythagorean identity, one of the identities I can do is I can convert cotangent squared into a cosecant squared minus 1. And by doing that, I know that there is a trig function that has a cosecant squared as a derivative. So knowing that to be the case, I know I can take an antiderivative of cosecant squared. So once I got it into this form, I recognize, okay, I know I can do the antiderivative of cosecant squared, and I made my u 3x and my du 3 times dx, did my substitution, and now remember, if I take the derivative of cotangent, the derivative is negative cosecant squared. So if I have the function cosecant squared that I'm trying to integrate, the antiderivative is going to have to be negative, since that cosecant squared was a positive. Okay, and then at the end, don't forget to plug in your u. Notice that I had a 1/3 multiplying to both of these terms down here. So since the 1/3 multiplies to both of those terms, when I plug the u back in, that 3x that would have gone right here got multiplied by a 1/3, and that's why you see an x to the first power there. All right, so there were a couple more here. Cosine cubed. So again, nothing really obvious on the surface. You just have to think through this a little bit. So I know that I can't integrate cosine cubed. I don't have a u and a du I can work with, so I have to start thinking about ways I can manipulate this. And what I did was I treated it as cosine squared times cosine. So with cosine squared, I can rewrite that as a 1 minus sine squared using a Pythagorean identity. And from there, now I can do my substitution. You can see I made my u sine, I made my du cosine x dx. And what looked really difficult now is a very, very simple integral to solve just with the power rule. Okay, so in the end, I got sine x minus sine cubed x over 3 plus c. All right, this is a really common integral that you're going to see over and over again with different exponents. But anytime you see a natural log of x over an x, once you've seen this one time, you'll be able to do this without even doing the substitution. You can just do it in your head. So I made my u natural log of x. My du is 1 over x dx. It may not be obvious that there's a 1 over x there, but since the x is in the denominator, I do have a 1 over x there. So I have everything I need. So this is essentially a u cubed once I do a substitution, u to the 4th over 4 plus c, and so I have natural log of x raised to the 4th power divided by 4 plus c. All right, and then the last one here, I put this one in here to make you think a little bit. You probably got stuck on this one, but if you did, that's totally fine. So on this one, I made my u 1 plus x squared. And so you might have thought through this and said, okay, if I made u 1 plus x squared and my du is 2x dx, I've got an extra x to the 4th here. I can't work with this. But the reality is we actually can work with this. And if you just kind of spun your wheels here and then finally gave up, once you see this one time, you'll think of doing this the next time. So I'm trying to deal with this extra x to the 4th that I have when I got this in the form that I wanted. So what I did was I rearranged my u expression and got an expression for x squared. X squared is the same as u minus 1. So that means that I can substitute that u minus 1 in for the x squared. And now, even though this is a little bit messy, I can do some algebra here, and I can come up with an expression in terms of u that I can then integrate using the power rule. So I ended up using the power rule. You can see that my antiderivative is a giant mess, but I was able to integrate that, even though at the very first part of this, it didn't seem like this substitution was going to work. So sometimes you're going to run into things like that where you've got to think outside the box just a little bit. And like I said, after you've worked with these a little bit and you've seen certain techniques used, you tend to think of them the next time you get stuck in those similar types of situations. Okay, in this last section, we've got some more of these integrals where the substitution is maybe not quite so obvious. And I just wanted to go through one of these where I go through all of the steps with you and make sure everybody's clear on how this would work. And then I'm going to have you try the rest of these questions. So on this problem, I've got the integral of x squared times the square root of x minus 1 dx. Now, when I'm thinking through this, similar to that last problem I just talked about, I'm thinking that u is probably going to be x minus 1. And if that's the case, that means my du would be dx. The problem that I have is I've got an extra x squared there. But now that I've seen that I've got a way to account for extra x terms within my integral, I'm going to continue on and actually solve this out that way. So I'm going to say u is equal to x minus 1. My du is dx. And remember, this is also telling me that x is equal to u plus 1. So with that being the case, that means this integral can be rewritten as, for the x's, I'm going to plug in u plus 1. So I have u plus 1 squared times the square root of u, or u to the 1/2, du. And then from there, it's just a matter of expanding this out and going through the integral process. So when I expand this out and then multiply by u to the 1/2, what I'm going to end up with, I would get u squared plus 2u plus 1, and then multiply by u to the 1/2. So I'm going to get u to the 5/2 plus 2u to the 3/2 plus u to the 1/2. Okay, du. And now I just have to do the power rule, and then I'm going to have to do some substitution at the end. So in the end here, with my power rule, I'm going to get 2/7 u to the 7/2 plus 4/5 u to the 5/2 plus 2/3 u to the 3/2. And then, of course, I have to remember my plus c. Okay, so at this point, I can plug in for the u. And again, just like that one I showed you a minute ago, the answer here looks kind of like a mess, but this is the indefinite integral, or the antiderivative of x squared times square root of x minus 1. So I have 2/7 x minus 1 to the 7/2 plus 4/5 x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2 plus c. So that would be my solution for that problem. And like I said, it doesn't necessarily look nice. Now I could do some factoring here. I could factor out x minus 1 to the 3/2, and I could make this look a little bit nicer. But that's not really, on these types of questions, I don't want you to get bogged down in all that algebra. I just want you to focus on the main idea of what we're looking at here is how do we get to that antiderivative. Okay, so there are 3 more questions here. One more like the one that we just looked at, and then there's a couple more that are a little bit different. So you have to think about what function does this look like it might resemble in terms of the derivative expression that you would have. So take a few minutes and try to work through these. And when you get to a point that either you've got them all or you're just stuck and you give up, I'll pause the video and I'll show you the solutions. Okay, so here is the next one. This is what you should have ended up with. So on this one, you would have made your u equal to x cubed plus 1. That means your du is 3x squared dx. So you're going to end up with an extra x cubed here. But we can get an expression for x cubed, and that's what you use for your substitution. And I just showed the result for this one. I didn't show all the steps, but it's basically the same process as the last 2 problems we looked at. Now, for these ones below, I showed you the main setup for these. So dx over 5 plus x squared. Now, this isn't exactly in the form that I want, but it's close. Now, when I see these types of questions, I'm recognizing that this sort of looks like the derivative of inverse tangent. The problem that I have is when I do the derivative of an inverse tangent, that number needs to be a 1. So since that number is not a 1, I'm going to rewrite this integral so that I have a 1 in that position. And then from there, I can do my Usubstitution. It becomes pretty apparent. So what I did was I factored a 5 out of the denominator, and I rewrote this as 1 over 1 plus x squared over 5. So if you think about this, this right here is essentially my u squared if I'm going to do an inverse tangent. So that means my u has to be x over root 5. My du is 1 over root 5x. So I've got to do a little bit of work there, but that's the main idea. And you can see in the end, my answer is root 5 over 5 inverse tangent of x over root 5 plus c. So again, these are really a matter of experience. The more of these you do, the more types of problems that you see, the more you're going to start to see these things right off the bat. You're not going to have to sit there and stare at the problem and try 3 different ways of solving it before you come up with a method that'll work. All right, and then the last one, this one is kind of like the one we just looked at with inverse tangent. When I look at this, my first thought is, and it's because I've seen a lot of these, my first thought is this looks a lot like an inverse sine derivative. So again, just like on the last one, that number on an inverse sine is going to be a 1. And since I don't have a 1 there, I'm going to need to factor that 25 out of the square root. When I do that, it becomes a 5. So that's where this 5 came from. But notice now inside the square root, I've got essentially 1 over square root of 1 minus u squared. So my u is x over 5, my du is 1/5. And so that 1/5 that I have outside the integral, I can just put it back in there inside the integral, and I end up with inverse sine of x over 5 plus c. Okay, so the big thing when you work through this assignment is that you just have to get practice with these. The ones that involve trig identities are always going to be the most difficult because you have so many options available to you. But there's really no easy way to learn this other than just getting experience with these problems. So practice, do all of them you can. If you get stuck, make sure you get in touch with me and I can point you in the right direction so that you can continue on with whatever problems you're stuck on.